Hello, chemistry class. This lesson is going to cover electronic transitions or electron transitions. And some basics about this is we are looking at wavelengths, and we're looking at the electromagnetic spectrum. That's the spectrum of light. And what we're looking at here is things that range from low energy, low frequency, or high wavelength radio waves that then become microwaves, infrared light, the visible light spectrum where we are able to observe colors, then the ultraviolet light, X ray region, and then the high frequency, high energy, low wavelength region of light, which is gamma radiation or gamma rays. And this shows that light from the top of a peak to the very next peak, or a valley to a valley. That's what we call wavelength. And for some regions of light, the wavelength can span the order of buildings or larger, and down to people or even the sizes of ants, unicellular life, all the way down to even viruses, atoms, and even the nuclei of atoms. So these can range quite a bit. Looking at our different parameters for the electromagnetic spectrum, we have wavelength represented by lambda, Lambda. That is the length between crest to crest on an oscillating wave, so the top of one peak to the next, or from valley to valley, the distance, the physical distance between one low point in a valley to the next. And the units of that will be meters. The symbol nu, Nu, which is basically a little fancy V, that will represent frequency, and that's how many times that wave is oscillating up and down per second. Now, since that's in units of 1/seconds, that's given the unit hertz, or Hz. Speed of light in vacuum, that's represented by c, lowercase c, and that's rounded to 3 times 10 to the 8th meters per second. Planck's constant H, represented with the symbol H, is 6.626 times 10 to the negative 34 joules times seconds, or Js. And then the energy of light, represented by E, we'll use the E symbol for energy. Connecting these parameters, C is equal to wavelength times frequency, or lambda nu, and then E is equal to Planck's constant times frequency, which happens to equal Planck's constant times the speed of light over the wavelength. And that's just another visualization of what we're actually seeing whenever we look at wavelength. That could be from a crest to a crest, or the physical distance between a valley to a valley of a wave. And hertz, even though it's in units of 1/second, we just represent that with Hz. So if you ever multiply a hertz by a second, that cancels out. And yeah. We also have prefixes, metric prefixes, a system of representing large or very small divisions of base units, whether that be meters for distance, grams for amounts, or liters for volume. We can modify them to go from liters to milliliters, or millimeters, milligrams, or if we want something less, or if we want to represent larger quantities, then we could do kilometer, kilogram, kiloliter, things like that. And one of the things that we're looking at here is our multiplier. We can essentially, an exameter is basically 10 to the 18th power number of meters. So 1 exameter equals 10 to the 18th meters, 1 millimeter equals 10 to the minus third meters. And these symbols here are just symbols that we would put in front of meter, gram, liter. For example, if we want milliliter, then that would be ml. If we want kilogram, that would be kg. So, doing some practice with metric conversions. Question 1. Light with a wavelength of 300 micrometers would fall within which region of the electromagnetic spectrum? Determine the frequency and the energy of this form of light. Question 2 is doing the same thing, but with a wavelength that's 1200 nanometers. And question 3 is doing the same thing, but with a wavelength of light that's 20 kilometers. Well, with the first equation, we have a 30 micrometer wavelength of light, so the lowercase fancy u, m, that means micrometer. In order to convert this to meters, we have to take 300 micrometers times 10 to the minus 6 meters per 1 micrometer. That came from this over here, 10 to the minus 6. Anytime we have the micro prefix in front of our base unit of meter, gram, or liter. So 300 micrometers times 10 to the minus 6 meters per micrometer gives us 300 times 10 to the minus 6 meters. Or if your calculator rounds things to, or puts things in scientific notation, then that would be 3 times 10 to the minus 4 meters. Moving the decimal over twice to shrink the value, we make the exponent more positive by 2. So 1, 2, increase that by 2, 10 to the minus 4. To get the frequency, that would be speed of light, our constant, divided by the wavelength we just solved for. Because our speed of light is in meters per second, that's why we want wavelength in meters. So 3 times 10 to the 8th meters per second, divide by parenthesis, 3 times 10 to the negative 4 meters, parenthesis, that gets us 1 times 10 to the 12th, inverse seconds, but if you have inverse seconds, then just replace that with hertz, Hz. Therefore, we have energy. That is just Planck's constant times the frequency. So 6.626 times 10 to minus 34 joule seconds multiplied by 1 times 10 to the 12th hertz. A second times a hertz cancels out, so we just are left with joules, and that becomes 6.626 times 10 to the minus 12. 10 to the negative 34 times 10 to the 12th, you just add the exponents together. Negative 34 plus 12 gets us minus 22. Wait. And then that might change a bit if this value is a large or small number that then gets converted to scientific notation, like what happened here to here, where that exponent gets slightly changed. Now, as far as our region of light, well, let's look at that. Our wavelength, we're looking at values that are 10 to the minus 4 in scientific notation, or energy that's 10 to the, or frequency that's 10 to the 12th. So 10 to the minus 4, that's looking at infrared radiation. Or 10 to the 12th for frequency, again, infrared radiation. I'm not going to test you on locating what region of light something is, but this is just to practice those concepts. Now question 2, the only thing different here is that now we're starting with 1200 nanometers. Going back to our prefix chart, a nanometer is 10 to the minus 9th meters per nanometer. So 1200 nanometers times 10 to the minus 9 meter per nanometer. That comes out to 1200 times 10 to the negative 9 meters, or in scientific notation, 1.2 times 10 to the minus 6 meters. Frequency would be our speed of light, 3 times 10 to the 8th meters per second, divided by what we just got in meters for our wavelength, giving us 2.5 times 10 to the positive 14 hertz. And then energy, we just take Planck's constant, 6.626 times 10 to the negative 34 joule seconds times our frequency. And that comes out in scientific notation to be 1.6565 times 10 to the negative 19 joules. And 10 to the 14 for frequency, or 10 to the negative 6 for wavelength. 10 to the 14, 10 to minus 6 wavelength or frequency. That's the visible light region, so that's going to be some color that we can roughly see, maybe closer to the lighter reddish orangish region. And then the third question was, what if we started with 20 kilometers? Well, then we would go 20 kilometers times 10 to the third meters per kilometer. And then that would end up being 20 times 10 to the third meters, or 2 times 10 to the fourth meters in scientific notation. So for frequency, we get 1.5 times 10 to the fourth power hertz, converted in scientific notation. And for energy, we get 9.9 times 10 to the negative 30th joules in scientific notation. 10 to the fourth meters, or 10 to the fourth hertz. Let's see. Or wait a minute. There we go. Let's see. 10 to the fourth meters. 10 to the fourth meters. That would be microwave radiation. So let's see if that frequency is actually correct. Yep, that all works out mathematically. So about radio wave length, more or less. Now to give some perspective, essentially an average punch, when we're talking about joules of energy, an average punch will have about 135 to 150 joules of energy in it, and that can still hurt. Now if it was someone who's a professional boxer, like Mike Tyson was, well, that's been known to clock in around 1,355 joules of energy, which has a lot of power to knock someone out. Now we're going to look at the hydrogen emission or the hydrogen absorption spectra, two different types of spectra. The hydrogen emission spectra would look like this, where essentially there are certain regions of light where hydrogen is emitting light because it had extra energy, and it's now releasing that extra energy at very specific points. We're going to notice that the opposite is an absorption spectra. That means, let's say we take hydrogen atoms and we start beaming light at that atom. Well, there are going to be certain regions where hydrogen is not absorbing the light, and then we can see it. But then the regions where we see blanks, that's where the hydrogen atom absorbed that light. But now if we turn off our light source, then hydrogen is no longer being bombarded with extra energy. What we see is now a bunch of these dark spots in the emission spectrum, because we are no longer just beaming a bunch of light on our sample. That means it has time to now release the energy that it absorbed during the absorption spectrum, and then we'll just see these lines now, these colors, in the emission spectrum. So these tend to overlap pretty well. Another way of looking at it is, to get an absorption spectrum, you have a light source that's on. A way of representing light is h nu, so energy of light is approaching our hydrogen atom. The extra light hits this electron and moves it to a higher energy level. So the energy that got absorbed, we're no longer detecting at the other end here. Now, once we turn that light source off, then we can get an emission spectrum where, as this extra energy in the electron now gets released back as light, allowing that electron to drop down an energy level. That light that was released is now what's being detected on our detector. So, absorption event, electrons absorb energy from light, going up an energy level, and in an emission event, an electron releases that stored energy and drops down an energy level. Now, there are specific types of electron transitions for the hydrogen transition, and they're based off of no matter what energy level that electron started at, what matters is what's the energy level that it ends at. So we have any series where where a hydrogen has an electron that drops to the first energy level. That's called a Lyman transition, and those are usually showing up in the ultraviolet region. If an electron transition goes from some energy level to the second, then that's going to be a Balmer series, and usually that shows up as visible color, like what we were able to see in our emission spectrum. If it's a Paschen transition, then it ends on the third energy level. If it's a bracket transition, then it ends on the fourth energy level. And if it's a Pfund energy level transition, then it ends on the fifth energy level. In using this, we're going to have our Rydberg equation, which is a formula for relating 1 over the wavelength, setting that equal to our Rydberg constant for our specific atom, in this case hydrogen, so RH, multiplied by parentheses 1 divided by the final energy level, NF squared, minus 1 over the initial starting energy level, Ni squared. A common error that happens when using this equation is either forgetting to square your denominators or taking the difference and then squaring it. What you are actually doing is taking 1 over the final energy level squared minus 1 over the initial energy level squared. And for our hydrogen atom, the Rydberg constant is 1.096776 times 10 to the 7th inverse meters. However, usually when using this equation, we want wavelength, which means whatever answer we get here, the total answer, raise it to the negative first power, or do 1 divided by this entire thing to get our wavelength. So as sample equations, sample problems, let's say for question 1, determine the wavelength of a Paschen transition originating from the 5th energy level. And question 2, determine the wavelength of a Balmer transition originating from the 9th energy level. Well, Paschen and Balmer. Paschen tells us that our final energy level is 3. Balmer tells us that our final energy level is 2. So for question 1, 1 over the wavelength equals our Rydberg constant, 1.096776 times 10 to the 7th, 1 over meters, times the quantity 1 over the final energy level. For Paschen, that's 3, so 1 over 3 squared minus 1 over 5 squared, the 5 being the energy level we were told that we started with. Now that ends up giving us 779929.6 inverse meters, which, taking this value raised to the negative first power, or 1 divided by this number, that gets us 1.28 times 10 to the negative 6th meters, which that's roughly near IR infrared to the visible light region. Now for our second question, we're just going to do this in one step, which you're welcome to do that too. Essentially these brackets here, just going to put the entire right side of our Rydberg equation in parentheses on your calculator, and then just have these additional parentheses as appropriate. So large parenthesis, Rydberg constant, times parenthesis 1 over our Balmer transition, which is 2, so 1 over 2 squared, minus our initial energy level, which we were told was 9, so 1 over 9 squared, parenthesis, large parenthesis, exponent -1. This lets us get our wavelength in one single calculation for 3.84 times 10 to -7 meters, roughly the visible light region of light. Now let's do electron configuration. Electron configuration, that is a method of classifying every electron in a given atom for a particular element. And here's our general pattern. We have our energy level. Our first number is our energy level. Then we have the block letter, which describes the type of electron we're looking at. This could be S, P, D, or F. And then we have as a superscript the total number of electrons in that combo, or the total number of electrons that we've picked up in this combo so far. So our block types, we have S block elements, P block, S block electrons, P block electrons, D block, and F block electrons. For S block elements, those are groups 1 and 2 on the periodic table, and also helium. Their energy level N equals their period number. The same thing is true for P block electrons. For an element that has a P block electron, they're gonna, for an element where its final electron is a P block electron, those are elements in groups 13 through 18. Now for D block elements, those are our transition metals. The energy level is going to equal the period number -1. And then for the F block elements, those are the lanthanides and actinides. Lanthanides are actually secretly part of period 6, and actinides are actually secretly part of period 7. The energy level of an electron, that's an F electron, is the period number -2. Now for S energy levels, they can only hold up to 2 electrons. P energy levels can hold up to 6. Each D energy level can hold up to 10, and each F energy level can hold up to 14 electrons. So just showing your periodic table, but with your orbital shell blocks, which if you're in my class, you should get a copy of this that you're welcome to have out during your tests. We have hydrogen here. That's part of the 1s block. It's the first element in that block. Helium is the second element in that block. So an electron from hydrogen, electron from helium. Lithium and beryllium, they're part of the 2s block. Then we have our elements here. Boron, boron, carbon, nitrogen, oxygen, fluorine. Those are all part of the 2p block, which each p block has 1, 2, 3, 4, 5, 6 elements in it. Once we get to our transition metals, we have our 3d block, so period number 1, 2, 3, 4. But for transition metals, the energy level is 1 minus the period number. And then for our lanthanides and actinide series, they start with lanthanum and actinium. There are 14 elements that are part of the lanthanides and actinides. They are secretly part of this intersection here, where the 4f block of elements shows up between the 6s block and the 5d block, where the 5f block shows up between the 7s and the 6d block. So 7th period, 7 minus 2 gives us the 5th energy level for our f block elements. Or if it's in the 6th period, then 6 minus 2 gives us the fourth energy level for our F block elements. S, P, D, and F, that basically represents the shape of the orbitals that those electrons are in. So as some practice, we're going to do electronic transitions, electronic configurations, also called electron configuration, for the following elements: hydrogen, helium, lithium, beryllium, carbon, fluorine, aluminum, nickel, zirconium, and bromine. We're not really getting into the F block elements for this class. That's more appropriate for a senior level inorganic chemistry course. Some people might take it during their junior year. I personally took it during my senior year of my bachelor's degree. So for general chemistry, we're just focused mostly on S, P, and D. So taking our periodic table of electron configurations, but plugging in the identity of some important elements. For the electron configuration of hydrogen, well, that is just the 1s position, and it's the first of the 1s block. Helium is also part of the 1s series, but it's the second element in the 1s series, so 1s2. For lithium, starting from left to right at the very top, to get the lithium, we go through the entire 1s series, so both elements, 1s2, and then we make it to the 2s series, 2s, but we're only in the first elements of the 2s series, so 2s1. So every electron along the way, that gets us 1s2, 2s1. Where 1s2, 2 is an exponent, then 2s1, 1 is an exponent. Beryllium is the very next element, so that's everything that we just had before, but now we're in the final position of the 2s block. So 1s2, 2s2. Carbon over here, we go through 1s2, 2s2, and now we're in the 2p block. Elements 1, 2, 2p, 2. So 1s2, 2s2, 2p2 for the entire electron configuration. Fluorine, we're going a few more steps further along. Same block as carbon, but instead of the second element in the 2p block, we're now in the fifth element of the 2p block. So 1s2, 2s2, 2p, 5. Aluminum involves us going through the entire 1s block, 2s block, 2p block, and 3s block. So now we're in the first element of the 3p block, or right here. So 1s2, 2s2, 2p6, 3s2, 3p1. Nickel, starting from the very top, going left to right, then going down a period, reading left to right. To get to aluminum, we go 1s2, 2s2, 2p6, 3s2, 3p6, and what I should say is I'm trying to get to nickel. Then we make it to our 4s2, and now we're in the D block, the 3D set of electrons. To get to nickel, we go 1, 2, 3, 4, 5, 6, 7, 8. So 3D 8. For zirconium, we make it all the way here. So to get to here, we go through 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d2. And then bromine, to make it all the way there, we have to go through 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p5. Now this gets pretty exhausting trying to write out the full electron address for these higher elements. So that's why there is a shorthand called the noble gas configuration. Basically, for any element that you want the electron configuration of, find the noble gas element that comes before this and then start writing your electron configuration. So for aluminum, the noble gas that shows up before it is neon. So we would write neon in brackets for our element notation, writing it in brackets, and then we'd start doing 3s2, 3p1. Right before bromine, the element that's in group 18 before bromine is argon. So bracket, AR bracket, 4s2, 3d10, 4p5. And for silver, well, the element that shows up before silver in group 18 is krypton. So then we would write krypton in brackets, then we would just write 5s2, 3d9. So that's a way of helping to write our electron configurations, but in our noble gas configuration shorthand. For this section, we have something called quantum numbers, and every individual electron in an atom has a unique set of 4 quantum numbers. The first is the principal quantum number. That's represented N, and that is the energy level an electron is residing in. Next is the orbital angular momentum quantum number. We represent this with L, and what that should be is L equals 0, 1, 2, all the way to n minus 1. So there we go. That should be L. The angular momentum L, it starts at 0, and it can get as high for a particular energy level to up to the energy level minus 1. So for the first energy level, 1 minus 1 is 0, so L can get as high as 0. For the second energy level, 2 minus 1, L can get as high as 0 or 1. These describe the shape of a, these describe the shape of a subshell and corresponds to our block type. Let's see. There we go. Each value for L represents a subshell of our total shell or our total energy level. Now the magnetic quantum number, this is represented M sub L. M sub L can range between negative to positive L, starting with the negative value. So if n equals 2, L can equal 0 or 1. And if we have a value of L equaling 1, then that can range from negative 1 to 0 to positive 1. If n equals 1, L can only equal n minus 1 or 0. Therefore, negative to positive 0 is just 0 for M sub L. Each individual value of M sub L is an orbital within our subshell. And then we have our electron spin quantum number, M sub S. That could either be spin up, which is positive 1/2, or spin down, which is negative 1/2. And this determines an atom's ability to generate a magnetic field or not. So just as an example, if we have an S block electron, the value of n is the period number. For every time that we have an S electron, that's the same thing as saying that L equals 0. Basically, there's a letter way to represent the angular momentum quantum number, S, P, D, and F, or there's a numerical way, 0, 1, 2, and 3. So S always means L equals 0. M sub L therefore can range from negative to positive L. Well, for an S electron, M sub L has to be 0. And then MS can be positive 1/2 or negative 1/2. For p block electrons, remember how we have 6 elements for every p energy level? Well, the energy level n equals the period number. L for any p electron is 1 every time. Therefore, M sub L can range from -1, 0, +1. 6 elements, there are 3 orbitals, so taking 6 divided by 2. But we can still have electrons that are spin up or spin down. For d block elements, the energy level n equals the period number minus 1. Anytime you see d, just think L equals 2. Therefore, M sub L can be -2, -1, 0, 1, or 2. And for the F block elements, the energy level is the period number minus 2, remembering that the lanthanides are really part of period 6 and the actinides are really part of period 7. Well, F is the letter way of saying L equaling 3. Therefore, M sub L can range from -3, -2, -1, 0, 1, 2, and 3. 14 elements divided by 2 gives us 7 individual orbitals. And then we have M sub S being positive 1/2 or negative 1/2 for the D block, the F block, the P block, or the S block elements. Some rules for while we're filling out our atomic orbital diagrams. We have the Pauli exclusion principle, which says that each electron within an atom will have a unique set of 4 quantum numbers. So between the values of N, L, ML, and MS, no 2 electrons will have the same 4 number combination of those quantum numbers within an individual atom. Hund's rule says that every orbital, so every M sub L, every orbital within a subshell, so within S, all the 3 orbitals within P, the 5 within a D subshell, the 7 within an F subshell, every orbital will be filled once with an electron before any orbital will be filled with a second electron. And orbitals will only ever be occupied by a maximum number of 2 electrons. So we're going to practice for a few sets of examples where essentially we're filling up the final atomic orbital diagram. So not the entire diagram, but basically the final electrons in that diagram for these atoms. So hydrogen, we have the 1s1, helium, 1s2, lithium, 2s1, beryllium, 2s2, boron, 2p1. We'll do those. Carbon, nitrogen, oxygen, fluorine, neon, that's 2p2, 2p3, 2p4, 2p5, and 2p6 respectively. Then vanadium and iron, 3d3 or 3d6. Nickel is 3d8, zinc is 3d10, and plutonium is 5f6. So I'm just looking at the final term in our electron configurations for all these elements. Practicing that, hydrogen, we have the 1s block, and it's the first element in that block. So we have 1 electron arrow, and if it's the first electron arrow in an orbital, we'll make that an up arrow. So we have 1 here, so n equals 1. We have s here, so L equals 0. That means that M sub L can only equal 0, and MS, if that's an upward arrow, then we write positive 1/2. For helium, that's also part of the 1s series, but it's the second element. So we have our first electron arrow up, going through hydrogen, and then at helium, we have the second electron arrow pointed down. The n value is still 1. The L value is still 0 for any s electron. M sub L is therefore still 0. But our final electron is negative 1/2 for the spin number because it's pointed down. Lithium is the first element of the 2s block, so it's pointed up. Its energy level is 2. Its angular momentum quantum number is 0. Its spin, or its magnetic quantum number is 0. And its spin is pointed up, so positive 1/2. Beryllium is the second element of the 2s series, so it's going to have its second electron pointed down. Same set of numbers as we had for lithium, except for the spin, which is now negative 1/2, because this electron is pointed down. Now we have boron, which is part of the 2p set. We don't just have one orbital now, we now have 3 possible orbitals, and we start from the left side first. The boron is the first element of the 2p series, so it has 1 electron that's part of the 2p series. We'll put that in the very left orbital. Now the energy level n equals 2. The L value, if we see a p here, just write 1. M sub L ranges from negative to positive 1. So negative 1, 0, positive 1. Those are our 3 orbitals. But our final electron for boron went into the negative 1 orbital. So M sub L equals negative 1. And because it's pointed up, M sub S equals positive 1/2. Let's look at some additional examples. We have vanadium. Vanadium right here, that's part of the 3D set. It's element 1, 2, 3. So 1, 2, 3. D blocks have 10 elements, so divide that by 2, we have 5 orbitals, ranging from negative 2, negative 1, 0, positive 1, positive 2. We have 3 electron arrows, so starting from the left, 1 up, 2 up, 3 up. This is the last electron we filled in, so we want the 4 quantum numbers of that one. N equals 3. L, anytime you see D here, just say L equals 2. M sub L, well, our electron here is part of the 0 orbital, so M sub L equals 0. And then MS, it's a spin up arrow, so it's positive 1/2. If we go all the way to iron, well, that's 1, 2, 3, 4, 5, 6 elements into our 3D series. So we fill up each orbital once. 1 arrow, 2, 3, 4, 5, and now we can start doubling up. Our 6th arrow goes into the first orbital, but it's spin down. This specific electron has the quantum numbers n equals 3, L equals 2, M sub L equals negative 2, just like as was shown here. And the spin is now pointed down, or negative 1/2. For nickel, that's now 1, 2, 3, 4, 5, 6, 7, and 8. So 1, 2, 3, 4, 5, 6, 7, 8. This electron here has an N value of 3, has an L value of 2. Therefore, these orbitals range from negative 2 to positive 2 for M sub L. But our final electron was in orbital 0. Negative 2, negative 1, 0. So 0. And it's spin down, so that's negative 1/2. Here for zirconium, Or, no, for zinc, I should say. For zinc here, that's the 10th element of the 3D series. So we have 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. N equals 3. L has to equal 2 if you see a D here. M sub L is positive 2 because negative 2, negative 1, 0, positive 2, positive 1, positive 2. This electron arrow is in the positive 2 orbital, and it's pointed down, so its ms value is negative 1/2. And then just to practice an F electron, or an F series, let's look at plutonium. Plutonium is right here. Starting with actinium, that's 1, 2, 3, 4, 5, and 6. There are 14 elements in our lanthanides and actinide series, so 14 divided by 2 is 7 orbitals. Starting from negative 3 all the way to positive 3. Plutonium is element 6, starting from actinium, 1, 2, 3, 4, 5, 6. So we have 6 arrows, we have 7 orbitals, so we fill up the first 6 orbitals with 1 upward arrow. Then we're going to identify the 4 quantum numbers for just this electron arrow. N would equal 5. L equals 3 if you have an F electron. That's basically the way of saying L in the letter version or L in the numerical version. M sub L, well, going from left to right, negative 3, negative 2, negative 1, 0, positive 1, positive 2. M sub L equals plus 2. And because it's the first electron arrow in this orbital, it's going to be ms equals positive 1/2. If we had enough electrons to have a downward arrow here to double up, then that would be minus 1/2 if it was a downward arrow. Just as a little note, what you see in this periodic table is 15 elements in this row and 15 here. In reality, lutetium and lawrencium, they're actually the first elements of the 5D and 6D block. So these 2 elements here are actually what are going here. The lanthanides are really lanthanum to yttrium. I think that's what YB is. And then the actinide series, as far as the F block, goes from actinium to nobelium. So just these 14 elements here are actually our F series. If you were at lutetium or lawrencium, that's actually a D block element. This is just a way of helping to organize everything and show that you go from barium, then lanthanum, then lutetium, then all the way here. Or you go from radon to actinium, all the way to all through the F block, then to lawrencium, which starts our 6D block, and then we go forward. In any case, glad to have had you all for this extra lesson on our transitions. Hope you're all doing well, and if you're in my class, glad to have you all. If you're just on YouTube, if I say subscribe to the channel, that should make the subscribe button glow like a rainbow. But as far as liking, subscribing, or commenting, you don't have to do that. But if you do, I'll probably heart it and comment back. Wish you all the best, and, well, as always, peace.